Today we're going to talk about what's called the central limit theorem, which is an important component that allows us to do probability calculations when we're talking about sampling distributions of the sample mean, or of X bar. So here we saw yesterday dealing with probability calculations and sampling distributions for X bar when the population was approximately normal. But in a lot of cases, populations aren't going to be approximately normal. And so we can still work through probability calculations in some cases because our population distribution being non-normal doesn't always mean that our sampling distribution won't be normal. So the central limit theorem kind of tells us under what scenarios we can look at a approximately normal sampling distribution. So here we can abbreviate the central limit theorem with CLT. That is an important abbreviation for you to recognize and use. And basically what that CLT tells us is that if our sample size is large, the sampling distribution for X bar is going to be approximately normal, regardless of what that population shape is. And again, being careful, it is the sampling distribution that we're saying is approximately normal, not the population distribution, not the sample distribution, but the sampling distribution. So the distribution of all of those X bar values. And so here we're going to see what is really our constraint for n being large. That size really depends on how non-normal the original population is. So if the original population isn't too far away from normal, you're going to be able to get away with smaller sample sizes than if your original population is bimodal or skewed. So here you have a histogram of a population data set that's clearly non-normal. You have a distribution that has 3 peaks. And so what we're going to do is from this population, we're going to look at sampling distributions of different sizes, but again, sampling distributions. So this again is the distribution of many X bar values. So if our sample size was just 2, we can see that that sampling distribution is still non-normal. Bumping it up to 5, still non-normal, but you have a little bit more of a mounding scenario going on, but it's still a little bit skewed. If we bump up our sample size to 10, we're getting closer to normal. And then down here with 25, that's getting reasonably close to a normal distribution in the sampling distribution, even though the population was very non-normal. So our guideline, or kind of our catch-all or worst case scenario, is that our sample size needs to be greater than or equal to 30. Again, in some cases in practice, we can get away with smaller sample sizes, but we're just going to go with n is greater than or equal to 30. That's kind of the convention for the AP exam because that's going to cover all of your bases. So even when you start with something that's as non-normal as this population up here, you're still going to get a resulting sampling distribution that's approximately normal. And so what this allows us to do is perform probability calculations on non-normal populations. So here's an example. I'll give you guys a minute to read that before we take a look. So here they tell us that the distribution is strongly right skewed for the population. But it then goes on to tell us that we are going to service 70 air conditioners. So our sample size meets that greater than or equal to 30 criteria for the central limit theorem. So we're going to go ahead and use probability rules to follow through the 4-step process and answer this question of whether or not 1.1 hours budgeted per unit is enough. So we have a couple of conditions that need to be verified before we do our calculations. We need to verify that the condition for sampling without replacement is met, because once you take one of these air conditioner service times out of the population, you're not going to resample it again. So you are sampling without replacement, which just means that the population size needs to be at least 10 times the sample size. So here we're servicing 70 units. We can safely assume that there's more than 700 air conditioners in the population. And again, this condition is for sampling without replacement. So we can go ahead and calculate the mean and standard deviation for the sampling distribution. Again, the symbols for this is important. So the mean for that sampling distribution is mu sub x bar. That's just equal to the population mean of 1. Standard deviation, or sigma sub x bar for the sampling distribution, population standard deviation over the square root of sample size. So here that's 1 over the square root of 70, or about 0.12. Now we know that this sampling distribution is approximately normal because our sample size is greater than or equal to 30. And the CLT, or the central limit theorem, is what tells us that. So even though the population is non-normal, our large sample size tells us that the sampling distribution from that population will be approximately normal. So here's a sketch of that sampling distribution. So again, centered at that population mean of 1. And then we can count up by multiples of that standard deviation for the sampling distribution, which was 0.12. And then again, we can count down by multiples of the same. The question here was, we budgeted 1.1 hours per unit. So it's going to be about here. We want to know if that's going to be enough time. So we're going to find the probability here, basically, that we were exceeding the 1.1 hours per unit. So we're going to be able to do that by calculating a z-score. So it is our sample mean of 1.1 minus our population mean of 1 over the standard deviation for the sampling distribution of 0.12. So our z-score here is 0.83, and then we need to go to either table A or the normal CDF function on the calculator. If you're working with table A, you would look up the 0.8 over here, 0.03 across the top, and you would find 0.7967 in the table. But again, that's the area to the left of your z-score, so we have to take 1 minus that value to find the area to the right. If you're using the calculator here, we would use that normal CDF function. Your lower bound would be your z-score of 0.83. Your upper bound would be 1 times 10 to the 99th. And then again, once you have a z-score, mu and sigma are just 0 and 1, or you can omit them when you're entering. If you're using the normal CDF in the calculator, that's going to give you this 0.2033 right off the bat. No need to subtract from 1. So if we budgeted 1.1 hours per unit, there's about a 20.3% chance that we don't have enough time to work within that range. So in section 7.3, it was all about the sampling distribution of the sample mean. Again, we just want to make sure that we're clear. We have this population distribution, which is the individual measurements for everybody in the population. The sample distribution would be the individual measurements for everybody in the sample. And then the sampling distribution is the distribution of all of the sample means. And so here, as long as we have something that is statistically sound, our mean of the sampling distribution is just mu, and then our standard deviation is sigma over the square root of n. Again, if you're sampling without replacement, we do have to verify that 10% condition. Before we do any probability calculations, we need to ensure that it's safe to do so, meaning that that sampling distribution is approximately normal. So really, you're looking at one of 2 criteria. Either the population needs to be normal, in which case then the sampling distribution is going to be normal. Or even if your population is not normal, the central limit theorem tells us that when your sample size is large, so again, we're going to use that cutoff of greater than or equal to 30, that sampling distribution is going to be approximately normal as well. So your assignment is to complete the bookwork. There is an optional Khan Academy on sample means and the sampling distribution and the CLT. And then you guys will have a 7.3 quiz, not tomorrow because today is Friday, so we'll say on Monday. And so for that 7.3 quiz, I would say expect a 4-step problem. step problem. So if you guys have questions as you're working on the homework, feel free to send me an email and let me know. I will get back to you if it's during the school day on Friday. And then we will have time to answer questions before the quiz on Monday.